The next topic is limit cycles. In a recursive system, when we apply the input as 0 or some non-constant value, some non-linearities will occur due to the finite precision arithmetic operations. These non-linearities may cause the output to oscillate. These oscillations can be a periodic oscillation, which means that the output of the system will oscillate between a finite positive value and a finite negative value for the increasing value of n. The output can also become a constant value if we apply zero input. Such oscillations are known as limit cycles. These oscillations are mainly due to the round of errors in the multiplication and the overflow in addition operations. Coming to the zero input limit cycles, consider we have a system and that system enters the limit cycle. It will continue in that limit cycle even though we apply the input with the 0. Such limit cycles are known as zero input limit cycles, which means that it is in the limit cycle and we are applying 0 as the input to the system, hence the name. The system will remain in its limit cycle until another input of sufficient magnitude is applied to drive the system out from the limit cycle. Next topic is deadband. Consider a first order filter. Next topic is deadband. Deadband is the amplitudes of the output in the limit cycle which are confined to a range of values. For a first order filter, consider its response as y of n is equal to a into y of n minus 1 plus x of n. The deadband will be 2 raised to minus b divided by 1 minus modulus of a, plus or minus. Here b is the binary bits used to represent the product, and for a second order filter y of n is equal to a1 into y of n minus 1 plus a2 into y of n minus 2 plus x of n. The deadband will be plus or minus 2 raised to minus b divided by 1 minus modulus of a2. Let us do a problem. Explain the characteristics of the limit cycle for the system described by by y of n is equal to 0.95 y of n minus 1 plus x of n. In this system here, the product is quantized to, let us say, 5 bits, including the sign bit, and the system is excited with the input x of n is equal to 0.75 for n is equal to 0 and 0 for n not equal to 0. So we have y of n is equal to 0.95 into y of n minus 1 plus x of n. And here we are taking the product quantization. We are not going for the overflow in the additions. So y of n can be rewritten as quantization of 0.95 into y of n minus 1 plus x of n. This is a recursive system. So consider I'm also having the input is equal to x of n, that is equal to 0.75 for n is equal to 0 and 0 n not equal to 0. When I start my system, the output will occur, and for n equal to 0, for n equal to 0, y of 0 equal to quantization of 0.95 into y of 0 minus 1, that is minus 1 plus x of 0. In my question there is no specifications of y of n minus 1, so we can take this y of n minus 1 as 0. Y of n minus 1 as 0. So y of 0 is equal to 0 plus we have x of 0, that is for n is equal to 0, x of n is equal to 0.75. 0.75. Since we have only 5 bits to represent the product, so for 0.75 into 2, that's equal to 1.5. I am converting this 0.75 to binary, that is 1. Next is 0.5 into 2, that's equal to 1.0, that is also 1. And the next 2 bits, 0 into 2, that's equal to 0.0, also 0 into 2, that's equal to 0.0. 0.0 into 2, we have 0.0. So 1100 is the binary version of 0.75, that is 0.75 plus 0.75 to the decimal is equal to 1 plus 0.1100 to the base 2, which means that 0.75 is converted to binary. When I am adding the sign bit, it will be adding sign bit. It will be, since it is positive, we are adding 0 as the sign bit. 0 1 1 0 0 0, and I'm quantized this value to 5 decimal points, including the sign bit quantizing. That is 0.1100. This is also in the binary. I'm taking back 1100 to decimal. That is 1 into 2 power minus 1 plus 1 into 2 power minus 2 plus 0 into 2 power minus 3 plus 0 into 2 power minus 4, that is equal to 0.5 plus 0.25 plus 0 plus 0, that's equal to 0.75 to the base 10. So this is, now let us consider the value at n is equal to 1. We have the output equation y of n is equal to quantization of y of 0.95 into y of n minus 1 plus x of n. When n is equal to 1, y of 1 is equal to quantization of 0.95 into y of 1 minus 1, that is y of 0 plus x of 1. We have y of 0 as 0.75. This is equal to y of 0. That is y of 1 is equal to quantization of 0.95 into 0.75 plus x of n is 0 now. Point 0.95 into 0.75, that is equal to quantization of 0.7125. 0.7125. So first I have to convert this to binary for representing in 5 decimal places. So 0.7125 into 2, that is equal to 0, 5, 2, 4, 1.425 and 0.425 into 2, that's equal to 0, 5, 8.0, that is 0.825 into 2, 5, 8 into 2, 16. So 1.650. I am taking 0.65. 0.65 into 2, that's equal to 1. Sorry here. This is 0.85. 85 because this is 8.85. So this will be 1.7, 1.70. I am taking 0.7 into 2, that's also 1.4, and 0.4 into 2, that's equal to 0.8. So 0.7125 to the base 10 can be represented as 10110 to the base 2, that is 0.7125 to the base 10 is equal to 0.10110 to the base 2. I am adding my sign bit binary sign bit. Since it is a positive value, 0 will be my sign bit. So 0.10110. I am quantizing this to 5 decimal points. So 0.1011 to the base 2. I want to convert this back to the my decimal value. Neglecting my sign bit. 0.1011, that is 1 into 2 power minus 1 plus 0 into 2 power minus 2 plus 1 into 2 power minus 3 plus 1 into 2 power minus 4. Here this is 0.5 plus this is 0.25 into 0, that is 0, plus 0.125 plus 0.0625. 0.5 plus 0.125 plus 0.0625, 0.6875. 0.6875 to the base 10, that is 0.6875 to the base 10. This is my y of 1. So now for n is equal to 2, y of n is equal to quantization of 0.95 into y of n minus 1 plus x of n. And for n is equal to 2, y of 2 will be quantization of 0.95 into 0.6875, 0.6875 plus here 1 minute, I skip one line. So y of 2 is equal to quantization of 0.95 into y of 2 minus 1, that is 1, plus x of 2. So here y of 1 is 0.6875 plus x of 2 that is 0, and point 95 into 0.6875, that is y of 2 is equal to quantization of 653125, 653125. So I want to convert this to decimal point, that is 0.65325 into 2, that's equal to 0.52726 remainder 1 12 13. I'm taking this one 0.306250 into 2, that will be 0 remainder 1 5 12 6. 0.6125 into 2 6125 0 5 2 12 0.225 into 2, that is 0.45. And also taking one more 0.45 into 2, that's equal to zero point 0.9. So 0.623125 to the base 10 can be represented as 0.10100 to the base 2. Six, 5. So 0.653125 plus to the base 10 can be represented as plus 0.1010 to the base 2. Adding my sign bit, since it is positive, that is 0.10100. I am negating the last bit, since we have only 5 bits to represent the number. So 0.01010 to the base 10, negating the sign bit 0.1010. I'm converting back to the decimal point. It is 1 into 2 power minus 1 plus 0 into 2 power minus 2 plus 1 into 2 power minus 3 plus 0 into 2 power minus 4, that's equal to 0.5 plus 0 plus 0.125. that is equal to 0.65, sorry, 625 to the base 10. This is now my y of 2. So for n is equal to 3, y of n is equal to quantization of 0.95 into y of n minus 1 plus x of n, that's equal to 0.95 into 0.625 plus 0. So that is quantization of 59375. Y of 3 will be quantization of 0.59375. So this will go on. So when we apply 0 as the input, the output will be in the certain limit. And coming to the dead band is equal to 2 raised to minus b divided by 1 minus a, since we have only since we have only the first order filter, which is 1 minus a, that is 2 raised to minus b. Here we are taking 5 bits to represent the product, so 2 raised to minus 5 divided by 1 minus, here a will be 0.95, that is equal to 2 raised to minus 2 raised to 5. 0.3125 0.03125 divided by 0.05. Point 625. So here for this particular problem, we will get the deadband as 0.625. So we will consider the values in between plus or minus 0.625 as 0. So actually this value will be 0. Okay. Thank you.